Hello, guys. So in this video, we're going to be looking at the end of chapter questions for chapter 10. So the first one is going to be question number 48, which says, consider the following boiling point data. The boiling points of these compounds increase steadily from methanol to pentanol. Which type of intermolecular force is primarily responsible for the steady increase in boiling points from methanol to pentanol? So to figure this out, first we need to figure out what are the different types of intermolecular forces. So we have LDF, it is called London dispersion forces. Then we have hydrogen bonding forces, and then we have dipole-dipole. So the first thing we notice in all of these, that all of them in all of these compounds, that they all have a single OH um, molecule in all of them. That tells us that they all have hydrogen bonding, and they all have the same amount of hydrogen bonding because the OH isn't changing. So this is not the main cause. Second is dipole-dipole. So dipole-dipole depends on polarity. So if you take, for example, methanol is going to be like this. So they're all polar, but the thing is that the reason they are polar, it's all the same. It's the same um, OH molecule, and it is the same as you go down the line. Hence, is the same amount of dipole-dipole force. The last one is LDF. LDF depends on the size, and the one thing we can notice is the size goes up as you go down the table, which tells us there is more, the LEF is increasing as you go down the table. Hence, it means the boiling points are also increasing. So the intermolecular force responsible for this is going to be LDF, or London dispersion forces. Question two, question two or question 53, difluoromethane has been considered a replacement for Freon. The boiling point is this. The boiling point of that is that. Which of the following statements concerning these two compounds are false? Carbon is the central atom. So to really understand this, and we can to fully understand both this question, we need to first get the Lewis dot structure of both compounds. So for CFCH2 is going to be carbon in the center, hydrogen, fluorine, and fluorine. That is CF2H2, and we got the other one that is going to be carbon, same structure, fluorine and chlorine. So let's start off with B first. Okay, both compounds are gases at room temperature. This is true because the boiling points is like -56 and -29, which means at like 24 degrees or like at room temperature, they're both going to be gases. That is easy to figure out. Second is CF2Cl2 exhibits stronger London dispersion forces as compared to CF2H2. So over here, even though the structures look the same, and it looks like, oh, they're the same size, it actually is different because instead of having the small hydrogen molecules, we have larger chlorine molecules, and that makes the CF2Cl2 a bit bigger, hence also increasing London dispersion forces. So that's true as well. The overall CF2Cl2 exhibits stronger intermolecular forces as compared to CF2. So this is pretty easy to figure out as well, as it has a higher boiling point. It means that it takes a larger amount of force to break apart the compound, and that is going to be true as well. For last one is both compounds are polar, so both compounds exhibit dipole-dipole forces. So that is true again because over here we got two fluorine, two hydrogen. It's not the same electronegativity all around, making it polar and hence having dipole-dipole. For CF2, Cl2, it's the same thing, even though it looks like they're the same amount of electrons around. Electronegativity is different. and that causes an asymmetry and causes dipole-dipole forces. Last option we have is A, in which it says CF2H2 exhibits hydrogen bonding intermolecular forces. So this, if we did not have made this structure right here, we would not have known the right answer. Uh, and we can see from here that hydrogen isn't bonded to fluorine, it's bonded to carbon. So which means that it doesn't have hydrogen bonding. And that makes this statement false and the answer for our question. Moving forward, question number 111. Carbon tetrachloride has a vapor pressure of 213 torr at 40 degrees C and 836 torr at 80 degrees C. What is normal boiling point of C2Cl4? So for this question, we're going to use the Clausius-Clapeyron Calperon, Calperon equation, and we're going to use this equation to solve our question. So first of all, as we're going to be using R, which is going to be the gas constant, we're going to need 80, we're going to have to need 40 and 80 degrees C or any temperature to be in Kelvin. So let's take 40 first, plus 273.15 gives us 313.15 degree Kelvin. For 80 degrees C, we got 273. If you add 273 to it again, it's going to be 353.15 degree Kelvin. Now we can use these temperatures for our stuff. So gas constant, I also need to add, is 8.3145 joules per mole Kelvin. So let's input this into our equation. So natural log of 836 over 213 equals to delta H of vaporization that we don't have the value of right now. R is going to be 8.3145 joules per mole Kelvin, and these are torr. Sorry, I forgot to write. Both of them are torr. Multiplied by 1 over 313.15 Kelvin minus 1 over 353.15 Kelvin. So let's solve this out. So the natural log of 836 divided by 213 is going to be 1.367 equals to delta H of vaporization over 8.3145 joule per mole Kelvin equal multiplied by, if we solve this out, the answer is going to be, or the value is going to be 3.6169 E negative 4. So we are going to send this over, and that would give us 377 9.376 equals to the delta H vaporization over 8.3145. And we can figure out what delta H of vaporization is. That is going to be 31,423.6 joules, or we can convert it over to 31.4 kilojoule. So we got our delta H of vaporization value. So to find out the normal boiling point, we don't have the value of the boiling point, obviously. We have to find that out. What we do know is that it's going to be at 760 torr or 1 atm. So we're going to use 760 torr as our value and find our temperature from there. So it's going to be 760 over 213 equals to, now we have the value, 31.4 kilojoule. We also need to change the value of the R constant. So that's going to be 0.0083145 um, kilojoules per mole Kelvin multiplied by 1 over 313.15 Kelvin minus 1 over X, which is going to be the boiling point we are actually trying to look for. So let's solve this out. Natural log of 60 divided by 213 is going to be 1.27 equals to, let's solve this out, 3.14 divided by 0.00833145. That gives us 3776.535. And we don't need to FOIL this out yet because we don't need to mess with two X values rather than just one. This one will go there. That would give us 3.368 e to the negative 4 equals to 1 over 313.15 minus 1 over x. We're going to subtract this from this. That would give us negative 0.002856 equals to negative 1 over x. Negative cancels out. X is going to be negative, oh, sorry, not negative, 350.07 Kelvin. So that is our answer, but we need to convert it to Celsius. And how we do that is we just subtract um, 273.15 Kelvin from it. Answer is going to be 76.92 degrees centigrade, or we can round it over to 77 degrees centigrade. And that is our answer for question number 111. Moving over, last question is 125. The ice cube tray contains enough water at this degree centigrade to make 18 ice cubes at each have a mass of 30 grams. Tray is placed in the freezer, uses CF2Cl as refrigerant. Heat of vaporization is this. What mass of CF2Cl2 must be vaporized in the refrigeration cycle to convert all water at 22 degrees to ice at negative 5 degrees? So whenever we're talking about state change, we're going to use phase change diagram. And for this one is going to be T2Q or heat. So we start off at 22 and we have to end at negative 5. But we can't come directly down because of phase change. And so we have to stop at 0 degrees for it to work. And if you draw this out, so it's going to be to 0, it plateaus, it plateaus, and then it goes down again to negative 5. So we got Q1, Q2, Q3. Those are the phases. We start off at liquid, we stop here at liquid, we become solid here, and we go down to solid again. In this question, These equations, sorry, these formulas are going to be used. Is going to be MC cat for when it's just a temperature change, not a phase change. Then you got moles multiplied by delta H of fusion because it's becoming ice and not vaporizing. And the same goes for delta H of vaporization, just letting you know. Uh, delta H of vaporization, though, is equals to Q over mass. So let's start. First, we also have to need to find out the mass. Mass is going to be 18 multiplied by 30. It gives us 540 grams of water. So at Q1, we're going to use MC-Cat. So that's going to be 540 multiplied by C when it is liquid. So that is going to be 4.18 multiplied by delta T, which is going to be 0 minus 22 or just 22. The value we get is going to be 49658.4 joules, but we will convert it to kilojoules because there are kilojoules used later, and so it's easier for us to use this value in our next part. The Q2 is when it's gonna turn from liquid to solid. Um, fully, we're going to use moles per delta H of fusion. Moles is going to be 540, which is a gram or mass, over 18.02, which is molecular weight, grams, sorry, yeah, grams per mole. And we're going to multiply it uh, delta H of fusion, which is going to be 6.02 kilojoules per mole, I believe. This is why we changed this one right here because of the units. Value that we get is going to be 540 divided by 18.02. Multiply that with 6.02, and we get 180.4399. So 180.4 kilojoules. Last phase is going to be Q3. We're going to use MC-Cat again. So that's going to be 540 multiplied by now. So the C changes. It changes from being liquid to being solid. So we're going to use 2.03, and temperature is going to be from 0 minus 5 or just 5, and our value is going to be 5,481 joules or 5.481 kilojoules. So now we have total Q or total heat. Sorry, total heat enthalpy, I believe, or the energy we need, and we are gonna add all of these together. So that is 499, 49.66 plus 180.4 plus 5.481 kilojoules. So they're all kilojoules, so we can just directly add them together. We don't need to convert now. So that is going to be 49.66 plus 180.4 plus 5.48. 481. So the answer we get is 235.541 uh, kilojoules. So now we're going to use this as the value of Q over here to find out, uh, not we have that, to find out mass of CF2Cl2 needed. So that is going to be no, 235. We have been given the value of heat of vaporization, which is going to be 158 joules per gram. But as it's 158, we need to convert it to kilojoules per gram, which is going to be 0.158 equals to 235.541 kilojoules again over mass in grams. And the mass is, I divide it out, and we get 1490.76 grams, or I believe we can round it up to 1491 grams. And that is our answer. Thank you.